So we started talking about strong things reacting with weak things. Sometimes when strong things react with weak things, we end up with something called a buffer solution. Sometimes we choose to make up a buffer solution on its own without reacting strong things and weak things. Buffers are things that have the ability, solutions, that have the ability to resist dramatic changes, maybe I should put the word dramatic, changes in pH upon the addition of small amounts of acid or base. And that can be strong acid or strong base. A buffer can absorb the strong acid or base that you've added, and the pH won't change very much. If you add strong acid or base to water, the pH of water changes a lot. It's a very dramatic shift. But if you add strong acid or base to a buffer solution, it does not have such a dramatic pH change. So what is a buffer solution besides that's what it does? A buffer solution has to consist of a weak acid or a weak base and the salt of the weak acid or weak base. That's kind of a weird way to say that. Both must be present. That's true. But the way I like to think of it as it has to be a conjugate pair. So you can have a buffer made out of acetic acid acetate because that's a conjugate acid-base pair. You can have a buffer made out of ammonia and ammonium because that's a conjugate acid-base pair. You can have a buffer made out of lots of acid-base conjugate pairs. So using a generic picture, if we have HA and A-, those are conjugate pairs. So when both of them are present in appreciable amounts, that's actually kind of important too, it can't be a tiny amount. When both of them are present in an appreciable amount, that's called a buffer solution. So in a buffer solution, if you have equal amounts of conjugate acid-base pair, equal amounts of HA and A-, HX, X-, depends on where you take the figure from, this is going to have a certain pH value. If you add strong acid to that buffer, does that strong acid, can't write and talk at the same time, does that strong acid react with the HX or the X- in your buffer solution? Acids react with bases, so it means that the H+ you add is going to react with some X- in solution, that A- in solution, depends on how you want to say it. That increases the amount of HX you have in solution because you're creating HX, and it decreases the amount of X- because some has reacted away. The exact amount that's reacted away is exactly the same as the amount of H+ that you've added. Maybe you can see a little table forming in your head, a little limiting reactant sort of table. Conversely, if you add some OH-, which is strong base, that strong base will react with the HX from your buffer system, and it will decrease the amount of HX that you have and increase the amount of X-, so our seesaw swings the other direction. If you add strong acid to a buffer exists at a certain pH. If you add strong acid, you should expect the pH to decrease. But does it decrease dramatically? No! If it decreases dramatically, it's not a buffer system. You may have gone outside what's called the buffer capacity. Maybe that's too much for the very first slide on this video, but I already said it. If you add strong base, understandably, the pH will increase. It will become more basic. You now have more conjugate base than you have conjugate acid, so the pH shifts upward. But does it shift dramatically? No, that's what a pH does. It resists dramatic changes in pH. If we go back to our old days of a weak acid dissociates in water to form H+ and A-, or you could write it that a weak acid reacts with water to create H3O+ and A-. We're still doing this kind of thing. I don't mean to talk about that's old news and we're past it. It's just old news. We've done it before. These are both Ka expressions, right? Ka equations, I'm sorry. A Ka expression for, let's say, the second one. Let's say the first one. It's a little bit more what we're used to, kind of. The Ka expression looks the same, except for it's H3O+ versus H+. So what? We get that. This is unique. This setup is unique for a buffer system. Oh, tripping over all my words. Because in a buffer system, we have to know that we've got HA present, weak acid, and A minus present, weak base. Both of the conjugate pair have to be present in appreciable amounts in a buffer system. So when both of these are present, it allows us to do some special fancy shortcut manipulation stuff. Don't we love shortcut manipulation stuff? Yeah, remember how many quadratic equations we had to solve before we said, when k is small, x is small, we could forget that x. Yeah, we like shortcut manipulations sometimes. So if I take the negative log, bear with me, I know you don't love math, if we take the negative log of both sides, we get this. And why would I do that? Because in chemistry, the negative log is known as a p. Okay, that'll mean something in a moment. As you may remember from, I don't know, algebra class, pre-calculus, calculus, I don't really know where you learned this. I don't remember where I learned it, but I remember learning it. When you multiply things in a logarithm together, it's like adding logarithms. So we can make this thing into negative log of Ka equals negative log of H plus the negative log of A minus over HA. So that's just taking advantage of a logarithm rule. I didn't do anything fancy. That's just a rule of logarithms. Why would I do that? Well, the chemistry term for a negative log of Ka is pKa. The chemistry term for negative log of H plus is pH. So let me flip to a new slide just so that I have a little more space to write. pKa is equal to the pH minus the log of A minus over HA. So, okay, this is an especially useful equation for a buffer system, and the people that discovered that were Henderson, that's ER, and Hasselbalch. That's called the Henderson-Hasselbalch equation. It's usually written this way. pH equals pKa plus the log of AHA. That's how our textbook writes it. It solves it for pH instead of pKa, so all I did was add that logarithm on the other side. pH equals pKa plus the log of AHA. That's A minus over HA, base over acid. Henderson-Hasselbalch. That's how our textbook writes it. I'm going to lose some of you, and I apologize, but there's another way you might see it written that's exactly the same equation. They've taken advantage of one thing. The negative log, plus the log of A minus over HA, if I flip that upside down, flip this fraction upside down to be HA over A minus, that's like raising something to the negative first power. HA over A minus raised to the negative 1. That's all I did. Flip it upside down, raise it to the negative 1. Because one of those other weird logarithm rules is an exponent can be brought out front like a coefficient. So a second way you might see the Henderson-Hasselbalch equation written is pH equals pKa minus the log of Yeah, I know. Just be glad that we're not in person for me to do that with you. So plus AHA or minus Ha plus base over acid or minus acid over base. I don't care which you use, but you're going to have to use this equation again and again and again. When you recognize a system is a buffer solution, you can make your work much easier by using the Henderson-Hasselbalch equation. Okay, we're about to breeze through some examples and use this a couple of times. How do you recognize that you have a buffer solution in the first place? You have to have a conjugate pair present. Weak acid, weak base, both present. If you have weak acid and weak base both present, recognize it's a buffer. You don't have to do a whole equilibrium table to solve it. Can you do a whole equilibrium table and solve it? Yes, but you don't have to do a whole equilibrium table. You can take a shortcut when you recognize it's a buffer solution. Okay, more about buffers. What is the pH of a solution that's 0.1 molar HA and 0.1 molar A minus? 0.1 molar weak acid and 0.1 molar weak base. Well, I recognize that's a buffer solution, and if HA and A minus are equal, HA, A minus are equal, I get to cancel both of those guys out, because that would be log, or that becomes a 1, and the log of 1 is 0. Punch that in your calculator, I promise. The log of 1 is 0. So that means at this magic point where the concentration of the base and the acid, meaning the weak pairs here, the weak pair concentrations are the same, pH equals pKa. So if this buffer system, if this weak acid has a Ka of this, minus the log of that value, we get a pH of 4.42 for this imaginary buffer system here. Equal concentrations of acid and base, pH 4.42. If A minus is 10 times the concentration of HA, that means you've got more base than acid, your pH should be closer on the base end. Your pH should be higher than it was when the system had equal concentrations of both. You can actually prove that mathematically with substituting in a 1 and a 10 on this and plugging it in your calculator, but we got enough other examples to do. I'm not going to do it right here, right now. Okay, a solution of weak acid and conjugate base does something useful. It acts as a buffer solution, which means it prevents strong acid or base from changing the pH of the solution dramatically. If we imagine adding 5 milliliters of strong acid, HCl is strong acid, right? 5 milliliters of strong acid to water, just plain water. What's the pH after you've added 5 milliliters of 0.1 molar HCl to water? In order to find that out, I need to know how many moles slash what's the concentration of H+. So I'm going to say 0.005 liters times 0.1 moles of H+ per 1 liter because it's soluble. I said soluble, I meant strong. 0.0005. Sure, I could make that into scientific notation, but yeah. 0.005 moles of H+ divided by total solution volume in liters would give me the concentration of H+, and that makes my concentration of H+ 0.0048. Sure, 4.8 times 10 to the negative 3. To find the pH of that, pH is negative log of that thing, and negative log of that thing is 2.3. So if we had water that was a solution pH of 7, because it was neutral, and we had 5 measly milliliters of not very concentrated, on the spectrum of concentrated to not concentrated, that's not terribly concentrated, HCl, our solution went to a pH of 2.3. That means from 7 to 2.3, it had a change in pH of 4.7. That's pretty dramatic. pH is already on a logarithm scale. Yeah, that's pretty dramatic of strong acid, 5 milliliters of strong acid to water. So a buffer can resist changes in pH, dramatic changes in pH. So if we add 5 milliliters of strong acid to a 100 milliliter buffer solution that has equal concentrations of HA and A minus, the instant that we add it to solution, we get the H+ and A minus to react together to create extra HA in solution. But apparently I've animated something else. So this says, yeah, it's HCl is a strong acid, so we do a limiting reactant table. Yeah, I typed in lots of things. Yeah, our equation would be A minus plus H+. Remember, strong acids act as limiting reactants, so A minus plus H+ yields HA. Why did I write it that way? Oh, I don't know. Well, eventually this is going to animate. I guess I'm just going to keep on working without that animation over there. If I start with a limiting reactant table, that would be 0.1 liters, 100 milliliters, times 0.1 moles of HA per 1 liter. That's where I get 0.01 moles of A minus and 0.01 moles of HA. Really hate that I wrote it that way. We're going to pretend I didn't write it that way. HA and 0.0005 moles of HCl. That's really the same moles as the last time. Minus X. If I change minus X plus X. H plus is limiting, so I get no moles of H plus. But I still have a reasonable amount of A minus and a reasonable amount of HA that you can't really read. Reasonable amount of those. So I've still got a buffer solution at the end of my limiting reactant table because I've got some of the conjugate pair present, some of each of the conjugate pair present. Here's my animation. H plus and A minus react together to form lots of HAs, but you still have plenty of A minuses, so it's still a buffer solution. So you find new concentrations of your base and acid according to your limiting reactant. That means 0.0095 moles divided by 0.105 liters, divided by 0.105 liters. We get a new concentration of A minus that is 0.0908 molar, and a new concentration of HA, that's 0.1 molar. And we can plug that into our Henderson-Hasselbalch. It's still the same acid system that we're talking about, so the pKa is 4.42. Plug in my new concentrations of base and acid, acid and base. Note that I'm using the minus. Base over acid, dang it, acid over base, we get, ta-da, drum roll, a pH of 4.38. Is that right? Does that make sense? Should my pH have decreased when I added strong acid? Yes. Should it decrease dramatically? No. It went from 4.42 to 4.38. It only changed by 0.04. If you recall, the water, when you added the same volume of the same concentration to water, it changed by 4 pH units, 4.7 actually. This buffer system changed by 0.04. That's a tiny change, and that's what the job of a buffer solution is, to resist dramatic changes in pH. Our bodies are buffer systems. If our body pH gets out of whack, we're in trouble, right? Right. Okay, we got to pick up the speed here. One last scenario. What if we had 5 milliliters of 0.1 molar NaOH? That's a strong base. Strong base, we do a limiting reactant table. I should have said this first. Add strong base. Strong base is not going to react with A minus. Strong base reacts with the acid in solution, so those things are going to partner up. And as long as they have some A minus and some HA left over after the reaction, we still have a buffer system. The equation would be HA plus OH minus yields A minus and water. Anytime I have a buffer, if I add strong acid, my equation is going to look like that. If I add strong base, my equation is going to look like that. Am I showing you this because I think it's worth memorizing? Heck no. No way. But coming up with the equation is sometimes challenging for students, but I hope we've done enough practice of net ionic equations for that to not be the case. If you add acid, as in strong acid, it's going to react with the base from your buffer. If you add base, as in strong base, it's going to react with the acid from your buffer. Write your equation accordingly, recalculate your new concentrations, and use an equilibrium table if you really want to, or use the shortcut Henderson-Hasselbalch thing to calculate the pH at the end. Limiting reactant, first bit, equilibrium, second bit. It's really what we've been doing all along. I'm just telling you, if you recognize it's a buffer, you can do a shortcut. pKa values are useful in determining where a buffer operates. What the heck does that mean? This table that we've been using for a while now, we've probably not even noticed this column in the middle that says pKa. pKa tells you, are useful for telling you where a buffer can operate. What does that mean? Well, let's do a little bit of numbers crunching. A buffer can resist dramatic changes in pH, but it can only really do so within a certain range. So if I have 10 times as much acid as I do base, then I would say pKa minus the log of 10 times as much acid as I have base that becomes pKa minus 1, because the log of 10 over 1 is 1. Okay, wait for it. If I have 10 times as much base as I have acid, same equation, but I'm going to put in 1 over 10 this time, 10 times as much base as acid. That simplifies to become pH equals pKa plus 1. So over here, 10 times as much acid as base can adjust the pH by 1 unit, 1 whole pH unit. 10 times as much base as acid can adjust the pH by 1 whole pH unit. But if you have a ratio that's far outside of this 10-to-1 ratio, that starts to be too much, and the buffer can no longer absorb that much strong acid or strong base. So we say a buffer operates in the range of pKa plus or minus 1. So this buffer system, this is formic acid, this formic acid buffer system can operate around pH 2.74 to pH 4.74, pKa plus or minus 1. This ammonium buffer can buffer around pH 8.25 to pH 10.25. That means, I was going to say some more, but nope, I'm done. Right there. Plus or minus 1 is the pKa range where buffers operate best. Done. Okay, a sample bisulfite ion buffer was prepared in which the concentration of HSO4 minus was this and SO4 2 minus was that. What pH should this buffer exhibit? Well, pH equals pKa minus the log. Pick your favorite equation and stick with it. I sometimes do back and forth. It's not a good habit. Minus the log of I need to know the pKa of this buffer system. In our normal standard pKa table, that means find the row that has both of those things on it. So that's SO4 2 minus and HSO4 minus. It's got to have both things present on the same row for us to be talking about that system. So that's pKa 1.92 minus the log of, in this system, this one is the acid and this one is the base. So 0.85 over 0.16. All it is plug and chug, and we get, notes please, 1.19 is what I've got written down over here. The final resulting pH is very close to the pKa. That is always the case when you have a buffer system. The final pH is going to be within 1 unit of your pKa in general. Is it possible to operate outside that range? A little bit, but not a lot. Which of the following weak acids, in combination with its conjugate base, of course, would be the most effective buffer for controlling pH around 6.3? Okie dokie. HPO4. Well, it's saying as a weak acid, so that means HPO4 2 minus. HPO4 2 minus. Where are you? HPO4 2 minus. So we're talking about that thing as an acid. No, it buffers around 12.38. It's not that one. H2PO4 minus. H2PO4 minus 7.21. That's reasonable to be around 6.3, but it's really 6.2 to 8.2. So let's see if we have a better option. HCO3 minus. HCO3 minus. That means that guy acting as a base. 10.25. Sorry, that guy acting as an acid. My bad. 10.25. I'm thinking not that one. We're running low on colors here that you can still read through as a highlighter. H3PO4, 2.12. I'm going to say negative on that one. And the last one, maybe we can read through a red highlighter. H2CO3, 6.3. I think we have reached our winner chicken dinner. H2CO3 is the right answer. Because its pKa is 6.3, it's going to buffer really well around 6.3. Oh, we gotta pick up the pace. What is the ratio of cyanide to HCN needed to make a buffer having a pH of this? Well, our handy-dandy table here, pH equals pKa, and I'm going to choose the version that has base over acid this time, so that's log of cyanide, so that I don't have to do further math, over HCN, and if it's base over acid, that's aha, so that's plus aha. When you make discoveries, that's a positive thing. Aha, I found this thing. Yeah, I know. I do whatever I can to remember things because I hate memorizing things. 9.89 is the pH we desire. And cyanide, HCN buffer, cyanide, HCN, that's this line, so 9.4 plus the log of cyanide to HCN. And 9.89 minus 9.4, that's 0.49, equals the log of cyanide to HCN. And so if I 10 to the both of those sides, that makes my log go away. So 10 to the 0.49 would give me my cyanide to HCN ratio. If you had chosen the other equation, you would just have to do the reciprocal here. But yeah, 3.09 is the answer I get. What is that 3.09 telling me? It's telling me I need 3 times as much cyanide as I do HCN in order to achieve a pH of 9.89 when I make up this solution. I need 3 times as much base as I have acid in order to make this pH higher than my pKa. In order to make your pH higher than your pKa, you're always going to need more base. So if you had found a decimal number here as this answer, you did something wrong. Okay. Calculate the pH. Oh my Lanta, are we not done yet? Calculate the pH of 65 milliliters of a 0.2 molar this solution, and then recalculate. Well, okay. Number 1, NH3, NH4 plus solution. That's a buffer when both are present. So that's pH equals pKa. Sure. Plus log of base over acid. In this buffer system, that's NH3 over NH4 plus. Okay. pH, handy-dandy chart, tells me the pKa of this system is 9.25 plus the log of 0.2 over 0.2, so that's really plus the log of 1, which is really 0. So pH of the buffer system in the beginning is 9.25 because it's equal to the pKa. Recalculate the pH upon the addition of 10 milliliters of 0.1 molar HCl. Number 1, this is a strong acid, therefore limiting reactant table is necessary. Because it's strong, you must do limiting reactant. So we're going to write the limiting reactant stuff on the next page. However, let me calculate a couple of things on this page. 0.01 liters times 0.1 moles of H plus, strong acid here. And that leaves me 0.001 moles of H plus. Okie dokie. If I do 0.065 liters of my buffer solution times 0.2 moles of NH3 per 1 liter, that gives me 0.013 moles of NH3. And because it's equal amounts, that's also moles of NH4 plus, without me having to do more math, right? Right. So, we're going to flip to the next slide and start writing. We're adding strong acid, and strong acid reacts with the base of our buffer system. So our net ionic equation is going to be the base from our buffer reacting with the strong acid to make some extra NH4 plus in solution. Is there already some NH4 plus at the start of this reaction? Yes. There's 0.013 moles of this and 0.013 moles of that. And we add in 0.001 moles of H+. We're going to change by losing some of this and losing some of that and gaining some of this. X is going to be 0.001. So in the end, we will end up with 0.012 moles of NH3, none of this, strong acid, and 0.014 moles of NH4+. So we've now got more acid, conjugate acid, than conjugate base. So that automatically makes me know that my pH is going to go down and become more acidic than it used to be. Right? 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 Are you bearing with me? Are you holding on? pH equals 9.25 plus the log of, we need to find the concentration of NH3 and NH4. Well, I have a shortcut for you. I would divide by my total volume, which is, I think it's 0.7. Let me go back. Hold on. 10 milliliters. So 0.75. 0.75 liters. 0.075 liters. 0.012 divided by 0.075 divided by, can you follow me? 0.012 divided by 0.075 divided by 0.014 divided by 0.075. The cool news is dividing by the liters would cancel out entirely. So make sure you're paying attention when I say, even though this is supposed to be concentration values, the fact is you're dividing the moles by the same volume on the top and bottom of your equation, so you can actually insert moles directly. If that confused the heck out of you, I'm sorry, but we can turn it into concentration and we can roll with it like that. If you followed along with that, we can plug moles in directly, and we get that the pH, after the addition of 10 milliliters of strong acid, the pH becomes 9.18. Is that a dramatic shift? Not at all. Buffers can be a little tricky. I'm not telling you they're impossible, but buffers can be a little tricky. You need to identify in this buffer system who's the acid and who's the base. And if you add a strong thing to it, you got to know who it reacts with and write a net ionic equation accordingly. Then we'll do our standard limiting reactant stuff. And if at the end of the limiting reactant table, you still have reasonable amounts of the conjugate pair of weak acid, weak base, it's a buffer, you could use Henderson-Hasselbalch and make your life shorter by not having to do a whole equilibrium rice table thing. It's a lengthy one, but an important one.